All right, so let's put all this together and let's do some examples that'll kind of talk about the things that we will really face, or we are more likely to face. So let's start with page 252, number 60. If somebody wants to read it for us, please. Okay. Sarah will read it. She's there. Whatever. Don't worry about the figure. You'll find it. Okay. So we're still in the realm where we're going to draw pictures. So before, I'm going to call them M1 and M2, even though they call them A and B. I just think it's easier. Okay, so this is going to be our 1.6 kilogram object, and this is going to be our 2.4 kilogram object. So it should really look just like the picture. I'm just going to use the ones and I's that we've been using to solve the problem so far. Okay? And then V1I is going to be 5.5 meters, and V2I is going to be 2.5 meters. And which ways are my objects moving? To the right. Okay. So we'll let that direction be positive x, just because it makes our lives easier. Okay. And thank goodness, the block in back has a bigger velocity. Because what would happen if it had the same velocity as M2, or if it had a smaller velocity? They would never collide, and there would be no point. Yeah, if they had the same velocities, they would move together, and the distance between them would stay the same, or the distance between them would get farther apart. All right. So this is our before. And then they collide, which we believe, again, because of what the velocities are. There's my plus x. And afterwards, I'm going to have my M1. I don't know which direction it's moving. And I'm going to have my M2, which I know is still moving to the right, with a velocity of 4.9 meters per second. And this is my after. And part A asks me, what happens to block 1? Which direction is it moving in, and what's its speed? Or we could really just ask, what's its velocity? So I'm going to assume that V1F is in the positive direction. And this goes back to something that we used to do a million years ago, back in chapter 2, that I always assumed that my unknown was in the positive direction. And then if I was careful with my negative signs, if it popped out with a positive direction, ooh-hoo, I was right. If it popped out with a negative direction, I would know that I was wrong and that it was really moving in the negative direction. So, this is a collision. Do I know if it is elastic or inelastic? No. The only thing I know is that it's not completely inelastic, right? Because if it was completely inelastic, what would happen? They'd be stuck together, okay? And the problem does not say that they're stuck together. And the problem, in fact, gives me a velocity for one of them and asks me to find the velocity for the other. So in any kind of collision, what do I automatically know? The total momentum before equals the total momentum after. That is kind of like the whole point of momentum, is that I know it's the total is the same before the collision as after the collision. Okay. Now we could pull out those formulas that we were using, that we developed earlier today, but you probably didn't remember them, and we talked about not remembering them. And this is a situation where I really only need that one velocity. So I really only have one unknown, and I can really put it all together just myself. Yes. In an elastic collision, kinetic energy will be conserved as well. In an inelastic collision, only momentum is. And that's because you're losing some of that initial kinetic energy to things like sound. If you hear the balls click, if they're squishy objects and they're going to deform a little bit when they go together, even if it's just two rubber balls, they're going to deform a little bit and then bounce back, and so that takes energy too. Okay, so I know that my initial momentum is going to be equal to my final momentum. It's always useful to write down the momentum for each object. So I've got m1 v1i plus m2 v2i is going to be m1 v1f plus m2 v2f. There's nothing really to cross off because everything has a velocity. But I can pretty much just solve this for v1f. I've got m1 v1i plus m2 v2i. Those can still be vectors. Minus m2 v2f divided by m1. And then we just substitute everything in. And so you substitute everything in and tell me what v1f is. So Zoe gets 1.9, positive 1.9. Okay, so let's see what somebody else gets. That's what Casey got. Let's see. Maddie got 1.9. Priya, Sari, Gianni, did you do it? Okay, so we were careful with our positive and negative signs. So we know that it's moving in the positive direction, but the problem asks us for left or right, correct? So in which direction is the object moving? To the right. So they both start off moving this way, and even though they collide, they continue both moving in that direction. So how would I figure out if this was an elastic or an inelastic collision? No, because if they were moving stuck together, that would be a completely inelastic collision. You can still have an inelastic collision without the objects sticking together. That's what Casey and I were talking about, that you lose some of the kinetic energy to the sound. Maybe they click when they hit. If they have to deform, if they're not rigid objects that are just going to bounce off each other if they're in contact for a little while, very tiny amounts of time, but they're going to deform and then bounce back, and that takes energy. So how am I going to figure out, how can I evaluate this collision? Sari? Yeah, we can check and see if the kinetic energy is conserved. Exactly. So I think that's what, part C? So we can ask ourselves if the kinetic energy before is equal to the kinetic energy after. So that gives us 1/2 m1 v1I squared plus 1/2 m2 v2I squared. Remember that we're taking the speeds here. 1/2 m1 v1f squared plus 1/2 m2 v2f squared. Now we can still cancel out all these halves, which makes everybody's life easier. So Casey, Sari, and Elisa, you do this half. Priya, Gianni, Zoe, and Maddie, you do that half. And let's see if we get the same answer for, well, you get the same answer within your group, and you get the same answer for both sides. So what do we get for this side? 63.4 what? Joules. Gianni, what did you guys get? Excellent. So that tells us that it's elastic. Okay. Did you guys have an additional part to this problem? Is there another part that talks about the initial velocity being something else? Okay, then we'll just skip that for now, so that we can, yeah, if we could do 2 more things, that would be good. Okay, so let's try another one. Page 252, number 62. Yes, for this one you can read the whole thing. Okay, so we will take them separately, but we are going to answer both questions. So, for part A, again, we need to draw a picture for our before and our after. So what do I know about the before? And what else do I know? Yeah, but they have the same speed, okay? So this is going to be V1I, and V2I is going to be negative V1I, and we'll let that direction be positive. Okay. And what do I know about afterwards? Yeah, but what do I know about my picture for afterwards? Let's do that, and then we'll talk about the other parts. Which one ends up being at rest? Which is going to be which of my spheres? I would let it be M1. Okay. So my M1 is going to be at rest. And I'm going to assume that my M2 has to be moving then. What would have to be true if M2 was not moving? Nope. Well, I already know the velocities I know the speeds are the same and the velocities are in the opposite direction. So what would have to be true for M1 and M2 to be at rest afterwards? But these aren't going to stick together. They're going to... Nope. They have to have the same mass. Very good, Sari. Because if they had the same mass, what would the total initial momentum be? 0, right? Because I'd have M1 V1I going this way and negative M1 V1I going that way. And when I added them, they'd be 0, which means that the momentum afterwards would have to be 0. So if M1's velocity was 0, M2's velocity would have to be 0, right? So I'm not saying that that's the case. I just want you to think about what would have to happen. I'm going to assume, as I usually do, that V2F is in the positive direction. If I'm wrong, it'll pop out with a negative sign and life will go on. Okay. So now we can talk about what we know for an elastic collision. So what's one thing we know about elastic collisions? The momentum is conserved. Momentum is conserved for every collision. So I can certainly say that PI is equal to PF. What else can I say about elastic collisions? The total kinetic energy is conserved. So I can say that Ki is going to be Kf. Now, what's the equation for kinetic energy? 1/2 mv squared. So I don't want to have to deal with squaring my v's if I don't have to. You want to keep it simple. So let's start with the conservation of momentum equation. Okay. So that tells me, well, it tells me a lot of things. There's actually one other thing that I know for elastic collisions. What's the other thing I know? You got it, Gianni. Thank you. This one might be useful here because I have a whole bunch of velocities, but I don't necessarily know anything about them. I know some of their values, and I don't know a lot about my masses either. So these are, of course, are going to be vectors. And I'm going to call V1I V1I. What's V1F? 0. What's V2I? Negative V1I. And if I don't know what V2F is, that's okay. I'm going to assume it's positive. So this tells me that V2F is equal to 2V1I. Positive 2V1I. So our assumption that it was going to move to the right in the positive x direction was correct. And not only that, it puts all of my velocities in terms of V1I, which probably means I'm going to be able to do what? And then what? No. Well, I'm going to want to solve for the mass, but how is it going to help me that I can put all of the velocities in terms of V1I? I guess we'll just have to find out. Not this problem. So again, I don't want to have to deal with squaring stuff because who wants to deal with squaring stuff? So let's go back to our momentum equation. So the total initial momentum has to be equal to the total final momentum. So that's going to give me m1 v1I plus m2 v2I is going to be m1 v1f plus m2 v2f. Okay. Anything I can get rid of here? Okay, so I know that v1f is 0. And then I can substitute in for my v's, right? So I'm going to let v1i just be v1i. But what's v2i? Negative v1i. And what's v2f? 2v1i. Okay. So this gives me m1 v1i minus m2 v1i is 2m2 v1i. And what can I do? Yeah, but what am I really going to do? Not yet. It's screaming at you. I can cross off the v1i's. There's one in every term. That was the beauty of putting everything in terms of v1i, is that they would be gone. So this leaves me with m1 minus m2 is 2m2. What am I solving for? m2. I know what m1 is because I chose which of my spheres was at rest. And the sphere that was at rest after the collision was the 300-gram sphere. And I chose that to be m1. So that tells me that m1 is equal to 3m2, or m2 is m1 over 3, or m2 is what? 100 grams. Okay. I know we have 4 minutes, but I think I'm going to let you go. We will finish the rest of that problem tomorrow. We will talk about collisions in 2D. We will do that problem, and that will work because on Wednesday, when we've got a long, even though it's a shorter long, we can do the rocket problem.